Okay, we got vehicles moving in two different directions here. Let's see what's going on. They say we have a van that starts out 140 kilometers due north of a car. So here we are, V for van, C for car. That distance begins as 140 kilometers. But then the vehicles start to move. The van moves west at 60 kilometers an hour. And the car moves due north. So this distance used to be 140 kilometers, but the car's coming north at 50 kilometers an hour, so this distance is decreasing 50 kilometers every hour. And what they're asking about is the straight line distance between the van and the car right here, which I'm going to call capital D. Now, what's good about the way that they're moving, one of them going straight west and the other one going straight north, is that there's always a right triangle that we can build right here. And if they're always connected by a right triangle, that means the Pythagorean theorem will always tie together this distance, which I'm going to call x, and this distance, which I'm going to call y, and the straight line distance between them, which I'm going to call capital D. We can always say x squared plus y squared equals distance squared. If we differentiate this, we get a rate equation, and that should enable us to get some work done. The derivative of this is simple enough. We get 2x dx. From the next term, we get 2y dy. And from the last term, we get, a bit awkwardly, 2d dd. Now, all those terms are divisible by 2, so let's just divide the whole works by 2. Keep this uncluttered. And also divide the whole thing by dt, because we want to talk about rates per hour. So, x and y and d are actual distances in kilometers. dx dt and dy dt and dd dt are all distances over time, so they're going to be in kilometers per hour. Those are our units for this one. And what we're trying to find is at what rate is the distance between them changing. That's dd dt. How fast is the distance changing as the hours tick by? So we better be able to fill in all these other values. Let's see if we can. For x is this distance, and they're talking about, by the way, at 3 o'clock p.m., meaning 2 hours after this whole exercise started. From 1 to 3 o'clock, 2 hours have gone by. So the van, at 60 kilometers an hour, should be 120 kilometers west. dx dt is how fast that's increasing, which is 60 kilometers an hour. Plus, for y, we were at 140, then it went down 50, that would have made it 90, went down another 50, that would have made it 40 kilometers. That's our y distance. And dy dt, I'm about to do something wrong. What is it? What's wrong with this dy dt? It's just a little thing. Y is shrinking. It started at 140, but it's going down, which means dy dt should be negative. Now, in some questions you can drop negative signs like that and get away with it. This is not one of those questions. We will be in large amounts of grief if we forget that negative sign, so please make sure that's in there. The straight line distance we don't have. Are we in trouble? Only a little. We can find it because of the Pythagorean theorem. It says, give me an x and give me a y, and I'll tell you what that straight line distance is. So x is 120 squared. Y is 40, also squared. Those together give us big D squared. So you will now hear my calculator working in the background. 120 squared plus 40 squared equals square root. I get that the straight line distance is 126.5, give or take, kilometers. That'll do for our distance. And finally, we have the dd dt that we're trying to solve for. So if we hammer all this out, we should be able to get dd dt. going to be, I'm going to calculate this entire left-hand side, and then I'm going to divide it by 126.5. So 120 times 60 plus 40 times negative 50 gives me 5200. Divide by 126.5, and I find that d dt is 41.1, and its units should be distance over time, so that should be kilometers per hour. This is positive, which tells us that at this point, the van is moving away faster than the car is closing the distance. That may not always be true. There may be some other places or other times where the distance between them is actually shrinking, but at 3 o'clock, it turns out the distance is increasing. And that was all they wanted from us. So many of these problems, especially if they involve distances, are going to come down to the Pythagorean theorem. Look for right triangles, always. You should always be able to set a right triangle between 2 points and describe its sides. And if you can do that, then you're well on your way.